Welcome to this lecture on the basics of neuroscience. Today, we're going to explore a truly fascinating topic called memory consolidation. Have you ever wondered how a fleeting thought or a quick glance at a textbook page transforms into a lifelong memory? Or why pulling an all-nighter often leaves you blank during an exam? The answer lies in a beautiful biological mechanism that acts as the brain's ultimate save button. Let us dive in and uncover how your mind builds its permanent database of knowledge. To begin our journey, let us use a simple analogy. Imagine you are typing a very important essay on your computer for a final grade. As you type, the words are stored in the computer's temporary memory, much like your brain's short-term memory. If the power suddenly goes out before you hit the save button, all your hard work is instantly lost forever. Memory consolidation is exactly like hitting that save button in your brain. It is the essential biological process that takes fragile, temporary information and permanently writes it into the hard drive of your mind, ensuring it survives any disruptions. Now that we have an intuitive understanding, let us look at the formal definition. In neuroscience, memory consolidation is defined as the time-dependent process by which recent learned experiences are transformed into stable, long-term memory representations. When you first learn something new, the neural circuits holding that information are highly unstable. They are incredibly susceptible to interference or decay. Without a stabilization process, new memories would simply overwrite the old ones or fade away completely. Consolidation is the critical bridge that takes these vulnerable traces and hardwires them into your brain's architecture over time. This stabilization does not happen all at once. It occurs in distinct phases. The first phase is called synaptic consolidation. This happens relatively quickly, usually over the first few hours after learning something new. During this time, a series of complex molecular and cellular events take place across the brain. Your neurons are literally changing their physical shape. This process involves gene expression and the synthesis of new proteins, which physically alter and strengthen the structure of the synapses connecting your neurons. It is the immediate, localized reinforcement of a new memory. Following the rapid synaptic changes, a much slower process begins, known as systems consolidation. While synaptic consolidation takes hours, systems consolidation can take days, months, or even years. During this extended period, the memory trace is gradually reorganized. Initially, the hippocampus is essential for holding the memory. But over time, the information is transferred and distributed to the neocortex, the outer layer of your brain. Once this transfer is complete, the memory becomes permanently stored and can be recalled even without the hippocampus. It is a massive structural reorganization of your brain's filing system. Why does this biological saving process matter so much in our daily lives? Without memory consolidation, you would wake up every single day unable to remember what happened yesterday. You would be completely unable to form new relationships, learn new skills, or build a continuous sense of personal identity. We know this largely from the famous amnesia patient known as HM. He had his hippocampus surgically removed to treat seizures. While his past memories remained intact, he completely lost the ability to consolidate any new memories. His tragic case proved just how vital this process is to human existence. This brings us to a very practical application of neuroscience, the role of sleep. Memory consolidation is highly active while we are sleeping. Your brain is not resting. It is busy replaying and saving the day's events. This is exactly why pulling an all-nighter before an exam is a terrible idea, as it interrupts the consolidation process, often leading to forgetting the material you just studied. Understanding this helps doctors treat memory disorders like Alzheimer's disease, and it helps students like you optimize study habits by prioritizing healthy sleep and spaced repetition. Now that we understand the biology, let us look at how neuroscientists mathematically model this process. While memory is complex, we can describe how memory strength grows over time using an exponential growth function. The formula is S of t equals S max times 1 minus e to the power of negative t over tau. Here, S of t is the memory strength at any given time t. S max is the maximum possible strength once fully consolidated. The symbol tau is the time constant, which tells us how quickly the brain is saving the memory. If you sleep well, tau is small, and memory grows quickly. If you are sleep deprived, tau increases, meaning it takes much longer to consolidate the same information. Let us see this formula in action with a concrete example. Suppose a student learns a new concept with a maximum memory capacity of 100 units. Under healthy sleep conditions, their time constant tau is 2 hours. We want to find the memory strength after 4 hours. We substitute 100 for S max, 4 for time t, and 2 for tau. The exponent simplifies to -2. The value of e to the -2 is approximately 0.135, which represents the fragile, unconsolidated portion. Subtracting this from 1 gives us the consolidated proportion. Multiplying by 100, we get a final answer of 86.5 units. Physically, this means 86.5% of the information is safely stored. Now, let us imagine the same student stays awake all night playing video games. Because of sleep deprivation, their biological save process slows down, increasing the time constant tau to 8 hours. The maximum capacity remains 100, and the time elapsed is still 4 hours. We substitute these new values into our formula. The exponent now becomes -4/8, which simplifies to -0.5. The value of e to the -0.5 is 0.606. This large number means over 60% of the memory is still highly unstable. Subtracting from 1 and multiplying by 100 gives a final answer of only 39.4 units. The memory strength has dropped drastically. Having calculated both scenarios, we can now mathematically prove exactly why sleep is so critical for learning. We will set up a proof to find the absolute loss in memory strength, which we will call delta S. To find this, we take the memory strength from the healthy sleep scenario and subtract the memory strength from the sleep-deprived scenario. We substitute the values we just calculated, 86.5 units for the healthy brain and 39.4 units for the sleep-deprived brain. This setup allows us to quantify the exact biological cost of skipping sleep. Continuing our proof, we subtract 39.4 from 86.5, which gives us a delta S of 47.1 units. To understand the true impact, we calculate the percentage loss by dividing this difference by the healthy memory strength of 86.5 and multiplying by 100. The result is approximately 54.5%. We have mathematically proven that depriving yourself of sleep immediately after studying destroys more than half of your potential memory retention. The biological save process was severely interrupted, meaning most of the studied material will likely be forgotten. Let us visualize everything we've learned by looking at this graph of memory consolidation. On the horizontal axis, we have time in hours, from 0 to 24. On the vertical axis, we have memory strength, capping at a maximum of 1.0. The horizontal dashed line at the top represents the maximum possible memory strength. Notice the solid blue curve representing healthy sleep. It rises steeply and safely secures the memory within the first few hours. Now, look at the dashed red curve representing sleep deprivation. It rises incredibly slowly. Even after many hours, a massive gap remains between the two curves. This visual perfectly illustrates how a larger time constant delays the biological save process, leaving your memories vulnerable. To wrap up our lecture, let us review the key takeaways. First, memory consolidation is the essential biological mechanism that acts as your brain's save button, transforming fleeting short-term experiences into durable long-term memories. Second, this happens in two main stages: rapid structural changes at individual synapses, followed by a slow, gradual reorganization across the entire brain. Third, we can mathematically model this growth to predict memory retention. And finally, as our equations and graphs proved, sleep is absolutely critical. Without it, the save process fails. Understanding this beautiful biological process empowers you to build a lasting database of knowledge.